Let's try our hand at one more example. And this is a little bit not as well behaved of a function, I should say. So this is another kind of function that we're looking for, again, the local extreme values, local extrema. So we'll use the first and second derivative test to analyze the behavior of the function. Before we go anywhere, however, let's first look at the general behavior of this function so that we can get an idea of what we're looking for. The first thing is we notice that it's a polynomial, right? Which means that the function's domain is all real numbers. It also means the function's well behaved, and in fact that its derivative is going to exist everywhere, right? It's a smooth function. So when we're going for the first derivative, we know that the only place we have to look for critical values are places for which the derivative is equal to 0, because the derivative does exist everywhere. So let's take the first derivative first. So computing the first derivative, we know this derivative is going to be x cubed minus x squared. Okay? And what I'm looking for are the critical values. So the critical values are going to be, again, the only place that's going to occur is where the derivative of the function is equal to 0. And we want to solve this equation for x again. Okay? So that means where x cubed minus x squared is equal to 0. I can certainly factor out a full x squared out of this, right? When I do that, I get something like x squared comes out. I get an x minus 1 is equal to 0. So the critical values occur at 0, right? If x were 0, the whole thing is 0, and at 1, plus 1. Okay? The critical values I've found is that c1 is equal to 0 and c2 is equal to positive 1. Okay? These are the x values for which the function has some kind of critical behavior, right? It's either going up, going down, or somewhere in between. Okay, something critical is happening. It's where the derivative is equal to 0. Notice, however, there's sort of a double root here, meaning that it's a square. Okay, that's going to always cause some kind of strange behavior, which is really why I chose this particular example. But let's go ahead and look at these critical values. And again, before we sort of determine or make an assumption that these are places where the function has a minimum or a maximum, we have to really use the first derivative test to find out whether or not they really are mins and maxes, right? So we have to look for the sign of the first derivative. So let's do that. So using the first derivative test, let's test these critical values. The first one is 0, and the other critical value is positive 1. These are just x values. And what I need to know again is the sign of the first derivative. So I'm going to put down the first derivative. Here's my first derivative as a function. And all I need to do is plug in one x value in this region, one x value in this region, and one x value in this region into the function to determine the sign of the first derivative there. Okay, so let's go ahead and do that. If I plug in a value over here, this is going to, let's just pick an easy one. How about negative 1? If I take negative 1 and I plug it into this function, I get that f prime of negative 1 is negative 1 cubed minus negative 1 squared, right? When I compute the value, I get negative 1 cubed is negative 1, so it's negative 1. Negative 1 squared is a positive 1, so you get a minus 1, right? That's negative 2, which means that the sign is negative. All I care about is the sign. Okay, so that means that the original function, if I draw it down here, is going down, okay, before 0. Now pick a point between 0 and 1. Let's say 1/2 to make it easy. So I'm going to take this point 1/2 and I'm going to plug that into the derivative. Here's my derivative. When I do that, I get a positive 1/2 cubed minus 1/2 squared. So when I do that, I get something like 1/2 cubed is 1/8 minus 1/4. But 1/4 is the same thing as 2/8, right? This is 2 over 8. Okay, the way I found that out was, since this is 1/4, if I multiply top and bottom by 2, right, that's equivalent to multiplying it by 1, I get 1/8 minus 2 over 8. Okay, that's definitely negative, right? That gives me a minus 1/8. All I care about is the sign, so that's negative. Whoops, something strange is happening here. the function is still decreasing after that critical value. Let's go find the sign of finally the third region in my domain, which is all the x values from 1 onward to infinity. Okay, so that means if I take the first derivative and I plug in some value after 1, let's say 2. Plug in 2 to the first derivative as a function. If I do that, I get 2 cubed minus 2 squared. That's definitely positive, right? Because it's going to be 8 minus 4, it's positive, right? It's positive 4, but it's positive nonetheless. So I see that the function actually goes up over here. So what we found is that even though these are two critical values, the function does not necessarily have a minimum or a maximum there. Okay? The function only has a local minimum at positive 1, but it has neither at 0. The function is just kind of flat there, actually. It's decreasing before and after x equal to 0. Okay? So this is a case where the first derivative, in some sense, the first derivative test sort of fails for this one particular 0 value, meaning that it's not a minimum or a maximum. And notice that what we're saying here is that f is decreasing on the domain, all the x values between negative infinity and 1. Right? It keeps decreasing, and f is increasing for 1 out to positive infinity. So it does have some kind of local minimum. Let's go ahead and compute the second derivative and test those values to find out the concavity of the function as well. And then we'll put it all together, sort of like all the king's horses and all the king's men, and we'll get an idea of what this original function looks like. Okay, so we know this is the behavior of the function. Let's go ahead and take the second derivative and test the second derivative function. So the second derivative is the derivative of the derivative. And you get, again, you're going to get 3x squared minus 2x. Okay, if I take the derivative of what we just had up there a minute ago. Okay? And what I want to do is, for the second derivative test, I'm looking for the concavity of the function. So I first of all need to look for inflection points. Again, this second derivative is a polynomial, which means that it exists everywhere. And so I only need to look for places where the second derivative is actually equal to 0. Those are the only places where the function may have an inflection point, but we still need to check. Okay? So solving for this equation, or solving this equation for x, I should say, I now get 3x squared minus 2x is equal to 0. I can pull a common x out of this whole quantity. I get an x outside after factoring this. 3x minus 1 is equal to 0. And I notice that there are two solutions, right? Well, this is 2, of course. Two solutions. First of all, x is equal to 0 would make this whole thing 0. And also, you can see that if this portion in here were 0, that is, if 3x minus 2 is equal to 0, that is 3x is equal to 2, so x is 2/3. Right? If x is 2/3, this is going to be 0 inside here as well. So my two places where the concavity may change, sort of my places I need to check, my critical values, are 0 and 2/3. These are critical values of the first derivative as a function. Okay? So I'm going to check and go through the second derivative test. So what I want to do is write down my pictorial number line here, put down 0 and positive 2/3. I'm going to plug these values into the second derivative as a function. Okay, and I want to find the sign of the second derivative. Recall again that if the second derivative of my function is positive for x values in some particular region, that means the function is concave up. And if the second derivative is negative, the function is concave down. Okay? The function is going to have a local minimum or a local maximum, depending on whether it's concave up or concave down. Okay, again, I'm going to go ahead and plug these x values before and after these two values I found, the two critical values of the second derivative test, okay, into the second derivative. So if I take, let's say, -1 and plug that into the second derivative, Well, here is the second derivative, right? If I plug negative 1 in, I get something like 3 times negative 1 squared minus 2 times negative 1. That's positive 3 plus 2. So it's positive. Okay. Similarly, if I take some value after that critical value, okay, over here in this portion of the domain, plug it into my second derivative as a function. Let's see what the sign is there. Let's say 1/3, right? So that's clearly in between. Plug 1/3 in, you get something like 3 times 1/3 squared minus 2 times 1/3. That's 3 times 1/9 minus 2/3. But this is the same thing as 1/3 minus 2/3, right? So it's negative. It's negative 1/3. So it's negative there. And similarly, I'm going to go ahead and plug in an x value over here in this portion of the domain into the second derivative as a function. Okay, when I do that, I have the second derivative of, let's say, 1, pick an easy value. That's going to be 3 times 1 squared minus 2 times 1, and that's going to be 3 minus 2, which is definitely positive. And I don't need to check any other values. I know that all the other values will have the same concavity or the same sign. I already know that because of how the test works. Okay? So the function is concave up here. It's concave down and concave up again. Okay? So we can go ahead and actually draw a picture of this since we have all the information we need. Let's go ahead and draw a picture of this crazy function. So drawing out this picture, I'm going to get an idea of how this looks. Okay, so there's my x and my y. Here's x equals 0. Something happens at 1, and something happens at 2/3. So if this is about 1/3, this is roughly 2/3. Okay? Notice how I'm going to break this function into different pieces of its domain. So something happens in this portion, happens here, that is. Okay, something happens over here, and something's happening at 0. So what's happening is, notice how the function is decreasing before and after 0. So the function is going down over here. It's still going down. It increases after 1. So after 1, it goes up. Okay, still decreasing up to this dotted line. The function changes concavity after 0. So it's concave up over here, in this portion of the domain. It's concave down between 0 and 2/3. See that? It's concave down over here. Then it's concave up again after 2/3. Okay? So let's go ahead and get a general picture of this. So what it does is, remember, it's decreasing here. So it's doing something like this. It's decreasing. And as it hits 0, it kind of flattens out right at 0. So it's decreasing up to the point of 0. It flattens out at 0. So you've got sort of a double root at 0. And then right at 0, it's gonna change concavity. So it's, remember, concave up means it's smiling. Concave down means it's frowning, and concave up means it's smiling again. So it's doing something like smiling, and then it goes down a little bit in between. Okay, it's got kind of flattens out here. It's going to have again a local minimum at 1, right? Because it's going down and then coming back up. So it's changing concavity to concave up. This is concave down now. Okay, it's concave down right before this portion. So concave down here. And then it changes to concave up again. Has a minimum. Then goes back up again. Okay, so that's what the function looks like. Okay, notice it's changing concavity, right? Concave up here, it's a smiley face. It changes concavity. It's concave down, a frown between here and here. And then it's a smiley face again. With a local minimum here, it just flattens out, does something kind of weird here. It has a critical value, but it's not actually a minimum, a local minimum or maximum, because the function is decreasing and then decreasing before and after. Right? It's going down before this 0, the value 0, and it's going down after 0. But before 1, it's going down and going positive afterwards. So I should draw this probably with a little bit more of a downward slope. Okay, so it's going down and then up after. Okay, so that's what this general function looks like. Not a great perfect picture of it, but it gives me an idea of what the behavior of the function is. And it shows you the power of the first and second derivative tests, and in fact the power of calculus.